Okay. Everyone's all chatty today. Chatty, chatty, chatty. It's nice. Is it because it's the last official chapter? I'm sad about it, but you're okay to be happy about it. So correlation, not that big of a concept, right? So we're just going to walk through it. There's a couple of little ins and outs, but you've probably heard about correlation, right? This is correlated with that. And it just means that there's an association or there's some sort of relationship, right? And so today, main learning objective is when do we use correlation? When is it appropriate, etc. We're actually not going to do a t-test for correlation. It's just a t-test, and so it's kind of back. We'll talk about what's the null hypothesis, what's the alternative hypothesis. But it's not actually easy to do in Excel, and that's the only time that you would do it. So what we're going to do is I'm just going to show you how to calculate the correlation using Excel after the slides, and then we'll leave the official hypothesis testing for another course. That's not this one. I don't know. Okay. So correlation is when we want to talk about, okay, is there a relationship between these two things, right? And one thing to keep in mind is that correlation, right, does not imply causation. And I had a prof who probably spent a whole term yelling that at us. Correlation does not imply causation. And so you can imagine that. Anyways, so I'll put it on here. I'm not gonna, well, I guess I did just yell at you, but in like a fake way. Stage yelling, let's say. So one important thing is that correlation does not imply causation. So that's a really important thing to keep in mind, right? Just because two things are correlated, right, it doesn't mean that one thing causes a change, right? They just happen to move together. And so as far as our null hypothesis goes, it's going to be the same as for a chi-squared. In fact, a chi-squared is a sort of correlation test, right? And so your null hypothesis, if we're talking about overtime hours worked and medication errors, kind of a big deal. Your null hypothesis is that there's no association between these two things. And then your alternative hypothesis is that there is an association between these two things. And so this is same as a chi-squared. So it's not actually a new null and alternative hypothesis. So some facts about correlation coefficient. So correlation coefficient is just the thing that captures the correlation, right? So the correlation. The correlation coefficient is a numerical measure of the strength and direction of a relationship, right? So if we just take it back a little bit, at the very beginning of the term, right, we talked about, okay, well, one way that we could visualize the relationship between two variables is a scatter plot. Right? And so we use a scatter plot to visualize the relationship between two variables. And so we've got some options, right? If we've got we'll just do a little recap here of, you know what, before we talk about, I'm just going to add a page in here. Add a page. And I'm going to scoot this over. Probably would have looked better if I drew it on a line, or if I wrote it on a line. Move it to the top here. Okay. So a scatter plot, just as a kind of a recap from way back when, is if we have something on the y-axis and something on the x-axis, right? The dependent variable goes on the y-axis, and our independent variable goes on the x-axis. Another word for the dependent variable is the response variable, right? And so this could be called the response variable as well. I actually prefer response and explanatory variable for the independent variable. Mostly because the explanatory variable goes on the x-axis. And so that's how I keep track of it, right? But in general, a scatter plot is going to look like something like that. Right. And so the correlation coefficient is going to be a numerical measure, so it's going to assign some value to the strength. So how close are these things moving together, right? So how closely related are they, or how what's the strength of the relationship, right? But also the direction. So if they're increasing together like this, you have a positive relationship. We could have something moving down, right? Whereas x is increasing, y is decreasing, right? So then we've got this opposite relationship, and that would be a negative relationship. And so what we have, if we look at just two plots in general, if we have a relationship like this, right, that would be a positive relationship. And same deal, but sloping downwards. Both of these are really strong relationships, but that's okay. This is a negative relationship. If we have, so positive or negative, there's no other options, right? And so then if we're talking about the strength of our relationship, then we could move from weak to moderate to strong, typically. Usually I just slice them and dice them it's either weak or strong, but then we often find ourselves, oh, it's moderately strong or moderately weak. And so if we have a relationship that looks like just completely random scatter everywhere, it's taking some time to catch up. Something like this, right? Then we have a weak relationship. I'm going to squeeze 3 graphs on here. I'm going to do weak, moderate, and strong. Let's see here. I'm not very good at doing the moderate one because it's like there is a relationship, but it's not that strong. Anyway, so here we go. Let me try. Sure. Here we have a moderate relationship. And then the one that I drew earlier, this would be a strong relationship. And so our correlation, right, it tells us, it gives us a numerical measure for whether it's positive or negative, right? That's just the direction, but also whether we have a weak relationship, a moderate, or a strong relationship, right? So it just tells us how things are moving. Yeah. So, and we'll kind of focus on linear relationships. So relationship is, if we had to describe this relationship, I would use a straight line, right? There's no reason to not use a straight line for any of these, especially this one, right? Definitely we would have to model it or describe it with a straight line, right? So that would be a linear relationship. Even here, right, we've got this kind of straight line relationship. And if there's a weak relationship, there's no telling where this straight line would go, but there's no reason to not use a straight line. So in most modeling, we'll have a linear relationship, right? And so that's kind of where we start, and it's the most useful and most applicable. But I digress. No, not really. It's very applicable. But let's talk about the correlation coefficients. So the correlation coefficient, right, we said is a numerical measure of the strength and the direction of a relationship. So it's going to range from -1 to +1. Okay? And so, and it can be 0. 0 correlation would mean there's no relationship, right? And a -1 is a perfect negative correlation, meaning that if you were to draw a straight line, the straight line would go through every single point, right? Same thing with the positive, right? Same idea, 1 being the strongest. And so if you drew a straight line through all the points, right, it would be a straight line connecting all the points. Oh. There's a couple of tests that we're going to talk about, right? The main one being the Pearson's correlation coefficient, or correlations rather, the Spearman correlation coefficient, and then we've already talked about the chi-squared, but it's also a correlation test. So we want to make sure that we have one independent sample. So our data has to be from the same sample. Are you looking for a linear relationship between 2 variables in the sample? So, or do we have a linear relationship? And whether we have a linear relationship or a nonlinear relationship, that's going to dictate which test to use. Okay, and it's on the next slide, otherwise I'd write it down. But and then, of course, what's your level of measurement? We are so hung up on that. But depending on what type of data you have, right, that's going to determine what tests to run or what correlation to calculate. Okay. So for our correlation coefficient, right, it's going to depend on the lowest level of measurement, right? Remember, we're comparing two variables, right? The relationship between two variables, right? And so if one is nominal and one's ordinal, right, we'd have to use a chi-squared. Even if one is ratio and one is ordinal, we would have to bump it up to a Spearman's correlation coefficient, and so on and so forth, right? So you just go for the lowest level of measurement. Chi-squared we've already talked about, and it feels familiar, but we use the chi-squared test to look for a correlation if we have an independent sample and the variables are both categorical, right? Categorical encompasses both nominal and ordinal. So we already knew that, right? We've only looked at 2x2 tables, right? Two outcomes, and then we looked at a cross tabulation. But remember, the chi-squared can be extended to multiple groups, right, or multiple categories, as long as you're looking at two variables, right? The relationship between two variables. The Spearman correlation coefficient is, and I'm just gonna jump right to it, okay, is if we have a non-linear relationship, okay? And so used if we have a non-linear relationship. So if we have something that looks like maybe something like that. Right. Even if you don't know what shape this is, right? And so if you keep going, or when you keep going in stats, say that, right? Probably if you keep going in stats, you'll learn what these shapes are, just like we know what a circle looks like and a square looks like, right? These distributions or these relationships all have names. But for us, right, we just need to look at this and say, well, it doesn't look like a straight line, right? So it's nonlinear. Right? Because if I tried to model this, right, or describe it with a straight line, it would actually do a really bad job at figuring out where the points would be, right? Which is the whole point of modeling. So let's use a different color here, right? If I fit a straight line through this, it would capture these guys and it would capture these guys, but it would do a terrible job elsewhere, right? And so here we say that this is a non-linear relationship. So if that's what you're dealing with, that's when you're going to use the Spearman correlation coefficient. We're not going to look at the Spearman correlation coefficient. We're going to focus on the Pearson correlation coefficient. For some reason, I feel like they're almost the same word, Spearman and Pearson. I think the same letter is just kind of jumbled, sort of. So I have a hard time keeping track of which one's which, and I've not got a trick for you, so I don't know. Just memorize it, I guess. But yeah, so the Spearman one is the one that we're not really going to focus on. we're going to focus on the Pearson correlation coefficient. But regardless, right, if we're looking at what level of measurement we need, right, we have interval or ratio level for the Pearson's correlation coefficient, and the Spearman can handle ordinal as well, so a categorical variable, but then another variable has to be either interval or ratio. And so but for us, the one that we're going to focus on is Pearson's correlation coefficient. Two normally distributed interval or ratio level variables, normally distributed in this case, is going to translate to a linear relationship. Which is on there, but pretty much all I want to say is already in the slides, but just writing it down. So Pearson's correlation coefficient is usually denoted by a lowercase r. Some textbooks will use an uppercase R or a capital R. So this is one scenario where the case doesn't really matter, which is weird because in stats we're all hung up on, oh, that's uppercase, lowercase, but anyways. So R is going to be our correlation, right? And so R tells us the strength and the direction of a linear relationship, right? So R is a numerical measure of the strength and direction of a linear relationship. Right, so it has that added caveat of, okay, we have to have a linear relationship. Any questions so far? So far, so good. Not really covering a lot of ground here, right? Correlation. It helps that we use correlation kind of in everyday language. Not necessarily every day, but in common language. A word you will use every day, homoscedasticity. Homoscedasticity. I don't know, I had a harder time saying specificity. Specificity. Homoscedasticity. Pretty similar. Anyways, homoscedasticity is just referring to, okay, well, one of the assumptions that we have for our correlation to apply is that we have to have even scatter throughout our plot. Okay? And so in order for R to apply, right, using R in place of the Pearson's correlation coefficient, in order for R to apply, we must have even scatter throughout our scatter plot. Throughout our scatter plot. So if we have, I'll just do a fake plot again, right? So if we have something like this, right, we've got even scatter or roughly even scatter. That's good. Use a little green check mark. Ooh. Whereas if we have a situation like, oops, that's why. If we have a situation like this, now I'm gonna need to focus a little bit. Whee. This would be, this would not be homoscedastic. I'll do a red X. No. Right. This would be a problem, right? Because our correlation is supposed to tell us the strength primarily, right, of this relationship. But the strength here is really high, right? And then the strength here would be not that high, right? And so, yeah, we can go ahead and the computer is going to calculate whatever you tell it to calculate, right? And so that's where it falls on us to have to check, okay, well, we're assuming that we've got homoscedasticity, even scatter around our line, right? And so if we don't, then we should kind of hold back on our correlation because it doesn't really apply, right? Because it's going to be different here, down here at the bottom, than it is up here at the top. Right? So that's all that's saying. I guess scedasticity must mean spread. Should have looked it up. Homo means the same, so that we got that one under control, right? Scedasticity. All right. So the strength of the correlation is going to be the absolute value of the correlation. Remember, the correlation goes from -1 to +1, but the actual strength, right? We said, okay, if we have a correlation of -1, we've got the strongest negative relationship that we could have. And if we have a +1, we've got the strongest positive relationship that we could have, right? And so the absolute value, are you guys familiar with the absolute value? It's where you drop the negative if you have a negative, right? So it just looks at, I almost said the absolute value, doesn't work, right? And so here, I guess it's down below. The absolute value is just the number of R, right? So we drop the positive, negative, right? Because regardless of the direction, right, the strength is going to have the same meaning. Dun, dun, dun. Were you guys like, what? When you read this in the chapter? And also very rewarding chapter, right? It was like, what, 5 pages or something? Yeah. Read chapter 11, check. Done. I was like, what? Why couldn't they say this earlier? And also, should I have known? No, not necessarily, because I don't deal with this stuff. So, the correlation is the effect size. Now, we know, okay, an effect size that's less than 0.3, right, we said was going to be weak. Between 0.3 and 0.5, we said would be moderate. And then anything larger than 0.5, we said would be strong. That's going to be the same for the correlation. Now, I can't remember. I did. I put it in the slides. Right? And so from the effect size, we know, and I didn't need that much room, but we know this, right? That a correlation, so R less than 0.3 is a weak relationship, an R between 0.3 and 0.5. Should have fixed that, but I really don't like when we use the little dash from 0.3 to 0.5. To me, it says 0.3 minus 0.5, which is not what you mean, right? So we should have, but I should have fixed that. Anyways, I didn't. Doesn't matter. And then anything larger, so a correlation larger than 0.5 is a strong relationship, right? Or we can write this as an R between 0.3 and 0.5. Got all that white space and I wrote it in there. Hang on. Just gonna rewrite that. Right, and so the correlation is the effect size, right? So, and because you already know about the effect size, you know a lot about the correlation as well. For example, right, if we have a small effect size, right, or a weak effect size, then we need a larger sample size to try to capture that, right? And so same idea, if we have a weak relationship, right? So if we have a small R, or we're not expecting to see a huge relationship here, then we would need a bigger sample size in order to try to capture that. So same idea. Cool, right? Any questions? No. We already talked about it, but a positive correlation relationship, right? So a positive relationship in general is when both variables are increasing together, right? Whereas a negative relationship is when one variable increases, the other one decreases, right? Vice versa. We saw that the chi-squared test, right, it doesn't tell us, okay, this one is going to be bigger than this one, right, or, right, it doesn't tell us what's going on. It just tells us that, hey, there's an association here that you need to look into, right? Same as the ANOVA, where it was just like, hey, there's something going on in here, right? And so a correlation does, or a correlation test does the same thing, okay, where it just says, yep, there's a correlation here, but I'm not going to be able to tell you which one is affecting which one, right? Or another way we can say it is that the correlation analysis is symmetrical, meaning that it doesn't tell you which one is increasing with what. That was vague. Whether A leads to an increase in B or B leads to an increase in A, right? It's not going to tell you that because it can't. Okay. Oop, what happened? There. So if we're doing a hypothesis test for the correlation, right? A hypothesis test is just saying, remember, the null hypothesis was, hey, there's no association between these two things, right? Meaning the correlation is not strong enough to be considered anything significant, right? Or the alternative is that, yep, there's an association going on here, right? And so that means that our correlation was strong enough to say that, yeah, there's something happening here, okay? And how we test it is software calculates a t-value. We could calculate it, but we don't have to. But in doing that, it would also get you a p-value, right? We know how t-values behave. We've seen them quite a bit now, right? And so we know with a t-value, we're going to get a p-value, right? So it's just going to produce that for you. Right? Even if you have a really high correlation, so a correlation of 0.8, for example, we know on our scale, right, from -1 to 1, 0.8 would be a really strong positive relationship. Even if we have a correlation of 0.8, right, it might not be significant if we have a small sample size, right? And so unless our sample size is big enough, right, even a strong correlation isn't going to necessarily be significant. And same idea, right? Small correlation coefficients could be mistaken for being significant if our sample size is really, really large, right? So we need a fine balance for our sample size, but that's just something to keep in mind. And so whatever you do, right, keeping this in mind, right, you're just gonna run your t-test for the correlation and then check the p-value, right? Everything hinges on the p-value. You're not gonna look at the correlation and say, whoa, that was 0.89, that's huge. Yep, that's significant. You have to do the test and check your p-value. All right. R² is the percent, so R², this guy, is the percent of variance, or the percentage of variance. So if you've made a scatter plot and you fit a straight line to it, usually in any report that you do, right, then, or read, probably more likely, they're going to report an R². Okay? And so R² just tells you how much of the change in Y is explained by a change in X. And so it is the relationship, right? It's basically just dropping the positive or negative. And in fact, if we square the correlation coefficient, then we get the coefficient of determination, which is your R². Okay? And so R² is the correlation squared. So what that's saying is that, and I usually use capital R². We could use lower R². Right? One of those rare instances where it doesn't matter. But R² is just the correlation squared. Kind of a side note, if I have R², I could take the square root of both sides and find the correlation, right? But I would need to look at my relationship to see if it's positive or negative, to tack that negative back on if I need it, right? Because that would be lost in the squaring. But it's not important, but it is an LFF, a little fun fact. All right, so here is kind of the definition of R². R² is the percentage of variability, so how much activity in Y, in the dependent variable, which is your Y, explained by changes in the independent variable, which is your X. Okay. And so essentially, how are these two things moving together, right? If X changes, how much does that explain the variability in how Y changes? Any correlation, so this is where we need to get really picky about whether we're talking about the correlation or the coefficient of determination, R², right? Because any correlation larger than 0.3, right, that's where we start talking about, okay, we have a weak relationship versus a moderate relationship, right? And so any correlation larger than 0.3, the start of a moderate relationship, is clinically important. Okay? So what that means is, okay, well, X, our independent variable, is explaining roughly 9% of the variance. Right? Because if you do 0.3 squared right? You're going to get 9%. So I'll do that here. Because decimals squared are kind of finicky. Make sure you get 0.09, but then as a percentage, right, you're going to have to multiply by 100. And then, so multiply by 100 to get the percentage. Because R squared is a percentage, right? R squared is the percentage of variability, right? So you have to convert it to a percentage. Oh my goodness, what time is it? Let's do some filler talk here. No, I'm not gonna waste your time. Oh, cute. I didn't see, did anyone see what it was? My nephew, he's just a baby. Yeah, anyways, R squared is the percentage of variability, right? And so usually I tell my students that, okay, as soon as you see, okay, there's the percentage of variability, blah, 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 blah. As soon as you see percentage of variability, it's talking about R squared, whether it's giving it to you or it's asking you to find it, right? Oh, I know what I was gonna do, but that's also gonna be really quick. It's gonna show you how to calculate the correlation. Yeah. But still gonna be done pretty soon. Okay, so any questions though, before we go into Excel, or I show you in Excel quickly? Oh. So next week, you don't have to do any readings, just come with an open mind. No, you already know everything you need to know. We're just gonna review it, right? And so we're gonna do a final exam review class. So everything you'll need, I'll bring. It might be a good idea because if I post like a Word document, then, because you guys bring your laptops anyways, you're all prepared. But then maybe it's easier if I don't print them out, because you'll run out of space for filling in those little blanks and stuff like that, right? So if you remember to bring your laptop, that's great. References, who cares? I mean, it's really important. All right, let me switch over here. You cannot start a screen share. Okay. Stop sharing. Start sharing. All right. Should have had it up. Anyways. I'm just gonna use that F Health Excel sheet that we had last day. So not a new sheet, because we can calculate the correlation between any two numerical variables. And one assumption that I am making is that I will have a linear relationship. Where'd it go? Whoa, zoom in. Wait. Come on. Somehow I did less. Okay, so remember this data set that we looked at last day, and we ran an ANOVA on the age categories and something else, I can't remember. If we want to know if there's a correlation between, and just for simplicity's sake, I'm just going to look at the wrist and the arm measurements. Wrist diameter, I guess, or circumference rather. So it is in the data analysis tool pack. So you're going to go data and then data analysis, and you've got the correlation option. So we're going to go there. And this is just going to calculate the correlation. So we need the input range, which I'm going to dive in here. And I'm going to include the labels up top here. The wrist and the arm, those are the guys I'm trying to find the correlation of. I have labels in the first row, and I'm going to put the output on the same sheet somewhere here and hit OK. So it tells us, right, that the correlation between the arm and the wrist is 0.6161582, for example. From what we know about our correlations, right, that would be a strong relationship, right, because it's higher than 0.5. And it makes sense that the correlation between the wrist measurement and the wrist measurement is 1, right? 100%, they're going to be the same. Same thing with the arm and the arm. And just for fun, let's just insert a scatter plot. So I'm going to highlight these guys. Oh. Highlight these guys. It's all glitchy when it's projecting, I think. You can insert a scatter plot. I would argue that it's a linear relationship. Not really, but maybe. Maybe I shouldn't have done that. No, I don't see any other shape, right? Is there homoscedasticity? Sure. We're pretty flexible on this kind of stuff. Unless it's like, whew, that's bad. But overall, I'd say there's random scatter around this line, right? We can fit the line of best fit, but that's regression, and that's for bonus mark day. How about that? So, any questions? No? Okay. Sorry, I don't know. My apologies. We're done. Yeah. See you guys next week.
We also work on these papers.
Oh, so pretty good time. Yeah. That is a relief, because otherwise I'm like, well, you guys probably waited around all day or showed up. Yeah.